We have been discussing construction of approximate trial state functions to describe for the description of electronic states of atoms, and we have stated that the approximate functions must have certain known properties of the exact solutions of Schrödinger equation. We had discussed, given the definition of the total orbital angular momentum, which is from here we have the z component of the total orbital angular momentum. Now from this we can construct square of the total orbital angular momentum, and we have stated that eigenvalues are L times L plus 1 in h bar square units for L equals 0, 1, 2, and there is no upper limit. Similarly, Lz, z components, eigenvalues are Ml, M sub L, which is constrained between L and minus L. This is for a given L value. And there are 2 times L plus 1 ml values. Okay. So this means that here, this is the Schrödinger equation for the electrons in any atom. H is the electronic Hamiltonian, and psi is the electronic state function. The exact solutions of this Schrödinger equation for psi must also be eigenfunctions of L square and Lz with such eigenvalues. In addition, there is the total spin angular momentum, which is defined as similar to this case. And the z component of this expression from here we can construct square of total spin angular momentum, and eigenvalues are S times S plus 1, where S is a total spin quantum number. You see, this is very exactly similar to this expression. where S max, maximum value for S is number of electrons divided by 2. This is the maximum. You see, in the case of orbital angular momentum, there is no maximum. But for the spin angular momentum, there is a maximum, which is number of electrons divided by 2. And all numbers which are smaller than this maximum in integer steps are allowed. Remembering that L quantum number and S quantum numbers must be non-negative. They cannot be negative numbers. Now, for the Z component, the eigenvalues are similar to what you see here. This time, we designate the eigenvalue by the capital M quantum number, but attach a subscript indicating that this is for the spin, ms. This is for the orbital angular momentum, in which we attach as a subscript capital L. So, all right. So, the exact solutions of the Schrödinger equation for any atom must also be eigenfunctions of S square and SZ. Let us remember what is the reason for it. S square, SZ commute with each other. They also commute with H. Therefore, eigenfunctions of H, which is psi, must also be eigenfunctions of S square and SZ. Similarly, L square and LZ commute. They also commute with H, and therefore the same, any solution of this equation for psi must also be eigenfunction of L square with one of these eigenvalues, and also LZ with one of these eigenvalues. In other words, exact psi is characterized by 4 quantum numbers. These are L, ML, S, and MS. It turns out that solutions, it turns out that the energy, the exact energies, depend on L value and S value, but not on ML or MS. Exact energies, E of this equation, depend on only L and S. In other words, not on ML or MS values. This means that for a given L and S, we have a certain energy. For the L value, there are 2 times L plus 1 ml values. This means, it means that there are, for the same L, there are 2 times L plus 1 different state functions. So it means degeneracy. The motion related to the orbital angular momentum is a motion in space. That one we describe as orbital motion. Do not confuse orbital motion with the concept of orbital. They are totally different. They have totally different meanings. The word is orbital. In one case, orbital is used as an adjective. Orbital motion. Word before motion is an adjective. It describes motion in space. On the other hand, when we use orbital as a noun, for instance, 1s orbital, 2s orbital, 2p orbital, there it is a noun. Its meaning is different. What does it mean? Orbital as a noun means a function. What kind of function? A function which is which contains the variables of just one electron. That kind of function is called orbital. So that is the word orbital used as a noun. But when we say orbital angular momentum, we are using it as an adjective, so it has a different meaning. It means motion, sort of rotational motion around the nucleus in space. Spin angular momentum, on the other hand, for a single electron, you may imagine spin as the electron in space as a point, then pass a axis, then it's a motion around the axis. There are just two possibilities. Either the spin is this way or in the opposite way. All right? So spin motion is different from the spatial motion. All operators that you see here for S depend on spin variables only. They do not depend on space variables. On the other hand, total orbital angular momentum and its Z component depend only on the space variables, but not on spin. Therefore, you should easily convince yourself that all of these operators commute with all of these operators. Why? Because they depend on different types of variables. All right. Now, because energy depends only on L and S, angular momentum characteristics of these state functions are displayed by a convenient notation of this type. Here is L, which is one of these quantum numbers. And then we attach the S as 2 times S plus 1. This is called term symbol or atomic term symbol. L written by its code letter. The code letters are the in numeric form, L values are, as you see over there, 0, 1, 2, etc. 0, 1, 2, 3, and so on. The code letters, capital S, capital P, capital D, capital F, similar to code letters for the orbitals. The difference is, as I said before, an orbital means just one electron. Whenever we are talking about properties of a single electron, we use small letters, lowercase letters. On the other hand, here we are talking about more than one electron, two or more electrons. In this case, we use capital letters, but the symbols are the same. Just the difference is lowercase letters for a single electron, uppercase letters for many electrons together. Now, energy depends only on L and S, we said, and therefore it is possible that there is spatial degeneracy. Spatial degeneracy arises from the orbital angular momentum characteristics, and spatial degeneracy is the number of different ML values for a given L. What is that number? How many different ML values are there for a given L value? 2 times L plus 1. A similar property occurs for a given S value. In this case, we may have many MS values. That describes the degeneracy because of spin. We call this spin degeneracy. And spin degeneracy is number of different MS values, which is similar to this expression. There are 2 times S plus 1 different values for ML. Therefore, this is the spin degeneracy. As you see here, in the atomic term symbol, we write the spin degeneracy as a left superscript. And we write the letter code for the L here. Let us have an example. Helium atom. Number of electrons, how many electrons are there in neutral helium? Just 2. N is 2. Then, what are the possible values for the total spin quantum number? Maximum value is number of electrons divided by 2. In helium, there are just 2 electrons. Therefore, maximum value for spin quantum number in helium is 1. Then you subtract 1 from the maximum, you get 0. And you stop there. Why? If you subtract 1 more 1, you get a negative number. No negative numbers are allowed. Total spin or total L quantum numbers are positive, non-negative numbers. So this means that spin quantum number for helium, we are thinking about all energy levels and the states of electrons, 2 electrons in helium. How many states can you imagine for the 2 electrons in helium? Infinitely many. All right? Starting from a lowest energy, ground state energy, there is no upper limit for the highest energy. In between, there are infinitely many states. So just imagine so many millions of states. These states can be characterized with the spin quantum number, total S. There are just 2 possibilities for all these infinitely many states. Roughly half of them are singlets, the other half are S equals 1. Okay, now, for the L quantum number, there is no restriction. L could be 0, 1, 2, 3, 4, and so on. So these same infinitely many electronic states are characterized according to the L value they belong to. L 0, 1, 2, 3, 4, and so on. And at the same time, according to S value they belong to. But there are just 2 S values possible for helium. So, now, for S equals 0, 2 times S plus 1 is equal to 1, isn't it? Spin degeneracy is 1 when S is 0. For S equals 1, 2 times S plus 1 is 3. We use words for these numbers, for the spin multiplicity. We call this singlet as a word. This one we call triplet. In other words, using these words, we can say this. The infinitely many different electronic states of helium are partitioned into 2 types with respect to spin. One part is singlets, the other part is triplets. It is the same thing as S equals 0 and S equals 1, but here we are using words. Now, singlets, we use the atomic term symbol. This is L value. And triplets, these are the possible term symbols for the electronic states of helium. You should also remember this. There are, as we said, when we consider all possible states of the 2 electrons in helium, there are infinitely many states, all right? Okay, these many states have term symbols, singlet S, singlet B, singlet D, and triplet S, triplet B, triplet D, etc. But it doesn't mean that there is just one singlet S term. In fact, there are infinitely many singlet S with different energies. Infinitely many singlet P, again with different energies. Same thing is for singlet D and all the other singlets. Similarly, for the triplets, same thing applies. So there are infinitely many triplet S states, infinitely many triplet P states. For each type, we arrange them in order of increasing energy. So, for instance, we write for the singlet S, the notation is we start with the lowest energy singlet S term. We assign number 1, the first one. Lowest is first, the next one is second, the next one is third, and so on. First singlet S, second singlet S, third singlet S, and so on. Similarly for singlet P and all the others. Again, the lowest singlet P we call 1, the first singlet P. The next one, 2 singlet P, second singlet P, and so on. Similarly for all the others. Okay? Now, for example, look at this. Such a energy level is degenerate. There are 2 causes for the degeneracy. One is this spin degeneracy. The second is the space degeneracy. Spin degeneracy you read directly from the superscript because this is 2 times S plus 1. So triplet D states are triply degenerate with respect to spin. But they are also degenerate with respect to L quantum number. Now, what is the numerical value of L for D? L, which number corresponds to D? 2. 2 times L plus 1. What is it? 2 times 2 plus 1. It gives 5. So, an energy level that has label triplet D is degenerate 5-fold with respect to space. It is degenerate 3-fold with respect to spin. What is the total degeneracy? Total degeneracy is spin degeneracy times space degeneracy. This. Total degeneracy of a term. So in this case, what is the total degeneracy? 3 times 5, 15. It means that there are 15 different functions, including spin and space variables. There are 15 different functions. All these 15 functions have the same energy. So the total degeneracy is 15. Okay, so far we discussed exact properties of this psi, which is an exact solution of the Schrödinger equation, regarding the total orbital angular momentum and also total spin angular momentum. There is one more, and in fact it is the most important property, exact property, which comes from Pauli exclusion principle. Pauli exclusion Now, previously, we mentioned Pauli exclusion principle in terms of orbitals. And we said that Pauli exclusion principle requires that maximum occupation number of an orbital energy level is this is the maximum occupation number of an orbital energy level. This is equal to 2 times g, where g is degeneracy of the orbital energy. For example, s orbitals, any s, 1s, 2s, 3s, etc. What is the degeneracy of an s orbital? How many s orbitals are there with the same energy? Only one. So, for s orbitals, the maximum occupation number is g is 1 times 2, it is just 2. On the other hand, if you take any p orbital, 2p, 3p, 4p, etc., p orbitals are degenerate. What is the degeneracy of a p orbital? P energy level, 3. In that case, maximum occupation number of a p orbital energy is 3 times 2, 6. But if you examine this more closely, you will see that in the case of p orbitals, the maximum occupation number is 6. It is because there are 3 p orbitals, p1, p0, p minus 1. Maximum occupation of each one separately is 2. So 2 plus 2 plus 2 gives 6. In other words, this simple statement simply states that for a single orbital, maximum occupation number is 2. So, a third example, for the d orbitals, d subshell, how many d orbitals are there? 5. For each one, maximum occupation is 2. 2, 2, 2, 2, 2. What is the total? 10. Here we say g is 5 for a d orbital, meaning number of d orbitals. Number of d orbitals times 2, it also gives 10. This is a simple rule here for the Pauli principle, but to discuss this equation, we need to give another definition, which is equivalent to this one, a more rigorous definition. Now, to explain the more rigorous definition, let us consider helium, electrons in the helium atom. We have just 2 electrons. Suppose this equation is written for helium, or 2 electron case. We label the electrons by integers, 1 and 2. Electron 1, electron 2. So, this notation means the psi in this equation is a function of 2 electrons. A function of 2 electrons means a function which contains the variables of the 2 electrons. In this case, these electrons are moving in 3 dimensions. The first, how many variables does the first electron contain? It has 3 variables to describe its location in space, but there is one more variable, which is the spin variable. It gives the spin state of the electron. Therefore, for the first electron, there are how many? 4 variables. For the second electron, there are also 4 variables. Total number of variables is 8. All right? 1 means here, the 4 variables for the first electron. 2 means another set of 4 variables for the second electron. Now, this notation, 2 first, 1 next, means starting with this expression, you are exchanging the electron labels. You are taking the variables of the second electron and putting it as the variables for the first electron. And similarly, you are taking the variables of the first electron and replacing the variables of second electron with those. That is what this means. According to Pauli principle, there must be such a relationship. This is Pauli exclusion principle. It means psi must change sign when the 2 electrons are interchanged. For interchanging, you may also use the word exchange. One goes to the place of the other, like this. This is the general statement of the Pauli exclusion principle in terms of the state function. Therefore, not any arbitrary psi function is physically allowed. In contrast, only those psi functions which satisfy this property are physically allowed. This is Pauli exclusion principle. Now, to understand, to get a better feeling about what this relation means, let us introduce permutation operator. Let me keep the Schrödinger equation here. The permutation operator. Now it means it exchanges labels of any 2 electrons in any function f(1, 2). In other words, take any function of 2 electrons, the action of p(1, 2) is simply exchange the labels. Make it this. This is the definition. Here f is any function of 2 electrons, or variables of 2 electrons. Now, notice that if you apply exchange operation twice to the same function, by definition, you first apply one by one. Now, what is the result here? F21 from the definition of the permutation operator. So the result is P12 F21. Now you apply to this function the same permutation operator. It will exchange once again. You will obtain F12. Do you see this? Now compare the starting expression and the final expression. What do you conclude about the net effect of P12 square? It's identity, isn't it? So we write P12 is equivalent to identity operator. It means, P12 square. In other words, P12 square does nothing to the function. The function stays as it is. Now, let us inquire about eigenvalues of P12. Let us assume that we have a function f12 be an eigenfunction of this P12 operator with eigenvalue P. What is the mathematical expression which this statement is telling us? We have a function, operator. What is the symbol for the operator? Remember, in our general discussion, we use A, but here it is more concrete. What is the symbol for the operator? P12. Equals function, same function, times eigenvalue. What is the symbol for the eigenvalue that this statement is telling us? P. This mathematical equation is the same thing as what this statement is telling us. Okay? Now, our problem is, what are the possible values for P? Which numbers are available for P? To get the answer, we make use of this property. So what we do is, we apply P12 to both sides. The left side becomes P1 square F here. The right side, because this P is a scalar, operator does nothing to it. Now, let us simplify. First of all, we know that this square of this operator is equivalent to identity. Okay? Therefore, we replace identity for P1 square on the left side, and then 1 times F is same as F. This is identity. Here, we simplify this part using the given information. F is assumed to be an eigenfunction of P12. Therefore, this can be replaced with P times F, but there is another P here. All right? So we have P square F. F is equal to P square times F. What can you say about possible values for P? The final result is this. F is equal to P square times F, and the question is, what is P? P is a number, remember. P is a scalar. P square has to be equal to, look, this is a scalar, this is a scalar, this is a scalar. P square must be equal to number 1, isn't it? If P square is equal to 1, what are possibilities for P itself? P is either plus 1 or minus 1. Therefore, what was our problem here? What are the eigenvalues of P12 operators? And we have reached a conclusion. What is that conclusion? There are just 2 numbers for the eigenvalues. One of the numbers is plus 1, the other number is minus 1. Okay, now come here. You see that if you take this psi12 and apply the electron exchange operator, permutation operator, if we get minus the right side psi21 is the net result of applying P12 to this is okay. What do we conclude? We conclude that the 2 electron function psi12 is an eigenfunction of P12. It is equivalent to Pauli exclusion principle, and the eigenvalue is what is this number? Minus what? Which number? Minus 1. So, Pauli exclusion principle is equivalent to saying that the psi function, electronic function of 2 electrons, must be an eigenfunction of this permutation operator, P12, but with which eigenvalue? Minus 1. The other eigenvalue is not allowed. The other eigenvalue is, what is it? plus 1. Plus 1 is not allowed here. All right, we take a break.